fail? I think it's time. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class, and thank you for the weekend and time to relax and refresh perhaps, or maybe just catch up on homework. And I just pray you be with us today. Help us to glorify you, what we do, and just to make the most of this time. Lord, in your name I pray, Lord Jesus. Amen. Excuse me. Still recovering from my cough. So in light of that, I'm going to preemptively chew some bubble gum. So. Do you guys have any questions about anything? Some guy carrying a table in the hallway. That's odd. So there is a quiz tomorrow. The quiz is on directional differentiation. Do you guys know how to do that? Like if I asked you to calculate the directional derivative of a function at a point, could you do it? Let's work an example. Example 1. Let's let f of x comma y equal to the inverse tangent of x squared plus y. Let's calculate the rate of change of f at the point, let's say, minus 1, 0 in the, let's say, 1, 8 direction. So we'll get started with that. So how do you answer this question? What do we need to calculate? How do we calculate the rate of change in a function? At some point, remember what we do is we calculate the directional derivative in the u hat direction, right, of f at the point P. Our formula for it was we take the gradient of f, we evaluate that at P, and we take the dot product with u hat, right? So first of all, the u hat needs to be a unit vector, right? So we need to figure out what that is. What's P? That's easy for our problem. It's minus 1, 0, right? That's the point we're asking about the change in, the function there. So it seems like the first order of business here is just calculating the gradient, right? So nabla f, in particular, we want to calculate the x derivative and the y derivative. So we're looking at what's partial x of inverse tangent of x squared plus y, right? And then partial y of inverse tangent of x squared plus y. How do we differentiate inverse tangent? What's that? Minus 1 over tangent squared? Oh no, definitely not. 1 over 1 minus x squared. No, not that either. So, like partial x of inverse tangent of u, for example, there's a chain rule here we would do, which would be 1 over 1 plus u squared times like partial u partial x, and similarly for y. So the derivative of inverse tangent is 1 over 1 plus the thing squared. Now if that's what you said, my apologies. I miss your thing sometimes. But okay, so the chain rule for the x component pulls out a what? My u, quote unquote u, is the input for the inverse tangent, which in this case is x squared plus y. So when I differentiate with respect to x, I get 2x. And downstairs, I get 1 plus parentheses, well, x squared plus y squared. Now you could FOIL that out, but there's really no point. I'd just leave it like that. All right? And how about next? Well, next we've just got 1 over 1 plus parentheses x squared plus y quantity squared. And why is there nothing in the numerator for the y component?
Derivative of y is 1.
Yeah, exactly. Partial u, partial y here is 1. All right, so that's the gradient for the function. Now we don't need, that's not what we put into the directional derivative exactly, right? We have to take that, we have to plug in the point, right? So let's do that next. Let's evaluate the gradient at the point. Oh man. Yowzers. I'd be careful, I'll get stuck down there. Gradient of f, plug in the point, minus 1, 0. So evaluating at that point. So we've got minus 2 over what? One plus what? 1 plus parentheses minus 1 squared plus 0 squared, right? 1 over 1 plus, and this time let me not write it out. What is that? I mean, that's 1 plus 1, right? So the denominator works out to 2. And let me just clean it up. Now, with the x's and the y's, I'd say don't clean it up. You're just going to plug a number into it in this problem, right? With the numbers, clean it up. Don't leave it like this. This would not give me joy. Anyway, so that simplifies to minus 1. Of course, the other one's a half, so we're stuck with that. Great. What's next? U hat. Is the given vector U hat? See this right here? This informs U hat equals to what? We need to take the vector and we need to normalize it, right? So U hat would be equal to 1 over the length of the 1, 8 vector times the 1, 8 vector, also known as 1 over the square root of 65 times 1, 8. Now, if you've got a fraction that's multiplying a vector and you're about to do a dot product, bringing the fraction or the whatever number, bring any number inside the vector would be foolish, because you're just going to end up multiplying and adding it again, right? It's much better for your calculation. Just leave this out here. Don't bring it in for this calculation. All right, so here we go. Directional derivative in my u hat direction of f at the point P, my so-called direct rate of change of f at P in the u hat direction, is exactly minus 1 comma 1/2 dot product with, I should have brought the 1 over the square root of 65 out to front, but I'll leave it there. It's a little bit ugly, but you guys can deal with it. So parentheses. So the 1 over the square root of 65 comes out front, and what do we get? We get minus 1 plus 8 over 2, because 1 times 1 is minus 1, 1/2 times 8 is 8 over 2, and of course that gives me what? 4 minus 1, so we get 3 over the square root of 65. There you go, that's the answer to this question, and this very well could be your quiz question tomorrow. Something like this, all right? So if you're rusty on differentiation, now would be a very good time to try to brush up on that. A good way to brush up on just basic differentiation is go to Stewart or your favorite calculus book and just work all the partial derivative problems until you're bored with it, right? Until you're completely refreshed on your partial derivatives. Now the quiz is open notes for you guys tomorrow, so I'll let you do that. Okay? Any questions? No? All right. Example 2. For f of x comma y equal to the same function, all right, a, if possible, find u hat for which the directional derivative and the u hat direction of f at, what was my point? Minus 1, 0 equals to, I don't know, 10. And then b, if possible. Find u hat for which directional derivative u hat of f at the point minus 1, 0 is equal to 0. And part C, if possible, find u hat for which the directional derivative of u hat of f in the minus 1, 0 is max. Part D, if possible, find u hat for, I really should have just like put a quote or something. Why am I writing this 5 times? Good grief. Anyway, so here it is. Min. All right, I finally learned my lesson. Quote is 4. So every one of these questions, we're not given u hat, right? And we're trying to find the unit vector which makes these, this particular dream come true, if possible, right? So it's useful to, we're just going to let u hat equals to AB for the discussion of this problem, right? And let's just let's just write down what is the formula for an arbitrary unit vector for this situation. The directional derivative in the u hat direction of f at the point minus 1, 0 by our previous work in the previous calculation is precisely AB. Well, I mean, I guess I can do the, what was I? Minus 1/2 dot AB, right? So what's the formula for arbitrary AB? You've got minus A plus B over 2. But what else do we have here? What's another formula that you can look at for the there we go. I heard a squared plus b squared equals to 1. That is true, not what I was looking for, but fair enough. A squared plus b squared does have to be equal to 1. It's a unit vector, but there's something else, right? Which is that this is equal to the magnitude of the gradient vector of f at the point minus 1, 0, right? Times the cosine of the angle. So if this is the gradient vector of f at the point, I guess I could actually draw it properly. What direction does it go? May not be a dummy. This we can graph. Minus 1 goes minus 1 in the right direction. So I draw a picture of what's going on here. We're minus 1 over and a half up, right? So it's something like this, right? This point that I'm drawing here would be minus 1, 0 in my picture, okay? So I could, theta here is the angle between, this and that. Not to scale, obviously, right? So that's another thing we have. Of course, we can be more specific. What's the magnitude of the gradient? Square root of 1 squared plus 1/2 squared, which is also known as 5/4, square root of 5/4. So square root of 5 over 2, I think. Do you guys follow me? So the length of this vector is 1 squared plus 1/2 squared, which is 1 plus 1/4, which is 5/4. The square root of 5/4 is square root of 5 over 2. So we have all these things. Now we can answer these questions, right? So how about, first of all, question part A. What's the answer to A? Can we have, so what is square root of 5 over 2 equal to, roughly speaking? Can you get, well, square root of 5 quarters, so 1.2-ish? Is that right? Somebody want to give me something precise to? 1.118. Okay, so I see now that I've asked the same question twice, right? Because the answer, as they're currently stated to parts A and part E, would just be no. You can't achieve a rate of change of 10 or a rate of change of 4, because the max rate of change is what? Right here. Because the biggest cosine can be is 1, right? For a dot product, the largest a dot product can be is when the vectors are parallel. It's just the product of the magnitudes. But U hat has length 1, so the magnitude of the directional derivative is just the magnitude of the gradient. So let me change part E to be, instead of being 4, let's make that a 1. That'll make it more exciting. All right. That's what I should have done there. Now, I was looking at the square root of 65 when I wrote down the 10. I was thinking that the gradient had like length 8 when I wrote that. That's why I did that, but sorry about that. Anyway, so part A, impossible, right? You know, the directional derivative of U at F at the point that we're looking at is less than or equal to approximately, you know, well, we don't have to be approximately, square root of 5 over 2, which of course is definitely less than, you know, less than 10. So we can't achieve that. How about B? What do we need? We need the dot product to be 0 in that case, right? So what are my choices? So we need to use U hat perpendicular to the gradient of F at the point minus 1, 0. So let's see here. We want maybe 1/2 comma minus 1, or minus 1/2 comma 1, right? This is that quote-unquote cross product in 2 dimensions I told you guys about. You just flip the components and add a minus on one of them. That gives you a vector which is perpendicular in 2 dimensions. Now, if you don't like this, this is just a trick. If you want to do algebra, so like this would be Emily's solution. She'd be like, well, I want minus A plus B over 2 equals to 0. So therefore, A is equal to B over 2. So my AB vector must have the form, what? A, B over 2, comma A. Did I do that right? Oh, see, I made a mistake in my trick. Look at that. It's good we did Emily's way. So this is B times 1/2, 1. Now, so that's the direction. Any of those vectors would be perpendicular, but the U hat, how many? There are just 2, right? There's this one, and there's this one, right? These 2 I just drew up here are the ones which are perpendicular. So to find those, so see, I made a mistake here. Do you guys see this? This should have been a +1, and this should have been a +1/2. My bad. We got to put a minus on both of them. That's what I would guess if I wasn't doing the algebra. Yeah.
And then for the answer, you have to normalize this?
Oh yes, we still have to normalize. So, but we need 1/2. Well, let me continue over here, and we do everything with algebra land. So over here in the algebra land, we need that b squared times 1/4 plus 1 is equal to 1, which tells me that my b has to be equal to what? 1 over the square root of 5 over 4, also known as 2 over root 5. So we either have u hat equals to plus or minus 2 over the square root of 5 times 1/2 comma 1. So there you go. That would be the answer to part B. Those would be the directions in which the rate of change is 0. The unit vectors which are perpendicular to the gradient. And again, just to review, you could either just set the equation for the dot product equal to 0 and work out what the relation between A and B is, or you can use my silly trick, which is just to, if you're trying to find a perpendicular vector in 2 dimensions, you just flip the components and change one of them by minus. All right? I didn't follow my own instructions in the first thing I wrote down. Okay? Now listen, check your answer, right? If you think this is perpendicular to the gradient vector, well, take the dot product with the gradient vector, make sure you're right? This dot that is minus 1/2 plus 1/2, which is 0, so we're good, right? Any questions so far? So really, all of these questions boil down to maybe something you haven't thought much about it before, which is, how does the dot product work? What are its possible values? What's its structure? When can it be big? When can it be small? What's the smallest it can be? What's the biggest it can be, right? So what's the min? What's the max? Part C here. Goodness gracious. So part C, max, that was supposed to be a when theta equals to 0, right? Which is to say that u hat should be parallel to the gradient of f, at the point. And so what is that? Well, that's u hat. So what's the length of the gradient vector? Well, we just figured it out. It's the square root of 5 over 2. So we do 2 over the square root of 5 to normalize it. Where's my gradient vector? Minus 1, 1/2. That would be, this gives the max. In other words, that's the unit vector that points in the direction of the gradient vector, okay? How about the min? You just do minus 2 over the square root of 5. And we should bring the minus inside. So like 2 over root 5 times 1 minus 1/2. This would be theta equals to 180 degrees, right? That's when the unit vector is anti-parallel. It's the opposite direction to the gradient vector. That gives you the minimum rate of change possible at the point. Yeah? Now finally, the fun question is part E, right? Well, I think part B was kind of fun, but part E requires a little bit more. Like part B, I can kind of cheat because it's equal to 0. I can use this flippy-flop trick I have. But for part E, I just have to do the algebra. Right, so for part E, I'm looking for, the directional derivative in the u hat direction of f at the point minus 1, 0, which we worked out to be minus a plus b over 2. I need that to be equal to 1, right? Where a squared plus b squared is equal to 1. So when I'm looking at this problem, I find it helpful to visualize the algebra I'm about to do in terms of a plane that we don't always draw. But you can talk about this. This is just a space that you can use for visualizing what you're doing, the AB space. See, in the AB space, there's a unit circle, right? A squared plus b squared equals to 1. And then there's this thing, which is a line, right? And what is that line? So here you've got, b is equal to 2 plus 2a, yeah? So I drew my picture poorly because my y-intercept's like way up here. But anyway, so the line looks something. I'm a dummy. Does that the line looks like? Yeah, what's the slope? The slope is 2, right? Positive 2. So it would go something like this. Here's b is equal to... Now, you don't have to even draw this picture, right? You can totally solve the algebra here without drawing the picture, but I find it helpful to draw the algebra because it encourages me to look for the reality that there are 2 answers. And it's also going to prepare me for just how much more subtle the problem is when we get to 3 dimensions. For the domain, not for the graph. Okay, so then, fine, how do you actually solve this? Well, just plug this up into here, right? And we get a squared plus parentheses 2 plus 2a squared equals to 1, also known as a squared plus 4 plus 8a plus 4a squared equals to 1, which is 5a squared equals to, uh-oh. Oh, it's a, well, wait a minute. I've done something wrong here, guys. Oh, there's an A. Never mind. It's okay. I didn't see this A here. I was seeing this as something squared equal to a negative number, which made me stop in my tracks. But it's not that. There's an 8A. So I have 5A squared plus 8A plus 3 is equal to 0, right? Aha. Well, thankfully we know the quadratic formula. So this is A is equal to minus 8 plus or minus the square root of 64 minus 4 times 5 times 3 divided by 2, which is to say minus 4 plus or minus, hey, that works out kind of nice. That's actually 64 minus 60, which is the square root of 4, which is 2. It's actually minus 4 plus or minus 1. Man, that feels wrong. Oh, thank you. Thank you. Goodness gracious. I shouldn't try to do anything at this time in the morning. Good night. It's like I'm getting a solution which has magnitude larger than 1. That's impossible here. My solutions must be smaller than magnitude than 1 because they're supposed to solve this guy right up here. So if you get a equals to 2, you're wrong, right? You have to did something stupid like me. This 5 matters. So minus 8 plus or minus the square root of 4, which is 2, over 10. All right, fine. So finally, we get either minus 10 over 10 or minus 6 over 10 for my A, right? Minus 1 or, minus 3 over 5. So what are my answers? My U hat equals to, well, if A is minus 1, that makes B 0, right? And what's the other thing? So if this is my A, so I have, 9 over 25 30 was to minus 12. So equal to minus 4 5. We this is right. And directional